an IIC alumni. So he has done his BSMS here, and then for PhD working on CMS. So he worked with Ahen, RWG's Ahen, and he also won the best PhD thesis award like last year for this thesis. And like from past 2 years, he's working as a postdoc at Brown University. And apart from that, he's also leading the B tagging and vertexing group at CMS. So he's one of the level 2 convener there. And apart from these roles, he has worked on fixed to CC analysis and also worked on this charm calibration, charm tagging calibration at CMS. And he's involved in more machine learning tools and technicalities, and he has written some review papers also. If you search for his name, you will be able to find some recent LS and CMS machine learning tools used in B-tagging specifically. So you will be able to find that. And he is here. He's visiting. He's actually on vacation. He's visiting Bangalore. So I asked him to come and visit up here. So he'll be talking about the machine learning in flavor tags, basically B-tagging. Mostly B-tagging, right? Let's see.
Let's see.
So let's hear from him.
Okay, thank you. Okay, so first of all, it's very nice to be back here. Many new faces, some familiar faces. Yeah, so like Joseph said, I'm going to talk about flavor tagging and the role of machine learning in it, and how machine learning has pretty much revolutionized the field here. And I'll try to highlight on how machine learning is being used here, and what future architectures, what future directions we can hope to go from here. And yeah, so here's an outline. So here's an outline. I'm going to introduce what flavor tagging is, and then delve into how machine learning plays into this. So by machine learning, we mean simpler architectures that were in vogue like a couple of decades ago, and also going from shallow neural networks to stuff that's as recent as transformers, and how these have transformed the way we do flavor tagging. And then, in addition to just having algorithms, one also needs to calibrate these algorithms, and machine learning has been recently used in that space as well. So some nascent developments in flavor tagging calibration with machine learning, and then I'll end with some outlook for the future directions, how we expect to go ahead with this. So, what do we mean by flavor tagging? So, at CMS or Atlas or basically any hadron collider experiments, quarks, gluons, and basically tau leptons that decay hadronically are often finite state particles, which we want to detect. So they are not detected as such, because you cannot really observe a quark or a gluon or a hadronically decaying tau, but you observe their decay products. So this is called hadronization, and typically when they have slight boosts of the order of GeVs, these are detected as a cone of particles, which is basically a cluster of particles that's shaped like a cone, and this is known as a jet. And in general, you just see a cluster of particles in a detector. You cannot say what it came from, or it's just a cluster of particles, it's just a jet. But there are subtle differences between heavy flavor jets that are bottom quarks and top quarks compared to other kinds of jets. Same goes for tau leptons. For example, a B quark hadronizes into a B hadron, and this B hadron has a size of a lifetime. It means it goes through the detector and then decays at a secondary vertex. So it moves some distance within the detector and then decays. So in the detector, you would see tracks that are originating from a vertex that's not the collision point, so a displaced vertex. So this is a signature of heavy flavor quarks, like bottom and top quarks. And therefore, you will see displaced tracks as well as vertices that you can reconstruct them into vertices which are also displaced. So these are typical signatures we want to look for. So by B tagging, we mean use these properties to distinguish B jets from others. Why we want to do that? Because in the Higgs sector, for example, Higgs has the largest decay branching fraction, that is almost 60% to Higgs to BB. So it's for Higgs searches, this is a very important finite state. Top quarks decay almost exclusively to bottom quarks. So if you have any top quark analyses, B quarks, you need to know if a jet is coming from a B quark. Then for new physics, there are several proposed particles that decay to, let's say, top quarks, to bottom quarks, to even Higgses. And to detect this, you also need B tagging, or basically to identify a jet coming from a B quark. Now, B tagging is the term that we used for several years because this is what we could do, let's say 10 years ago. But more recently, we generalized this, we call this flavor tagging because it's not just B's that we can discriminate from other kinds of jets, but also C jets. Now, C jets are just coming from charm quarks. Now, charm quarks have properties that are somewhere in between that of light jets and B jets. So, they also have displaced vertices, but not as far. Maybe they decay somewhere in between. So you see that there are different patterns that need to be recognized. So one can do in the same way one does B tagging, one can also identify jumping. So it's a very natural generalization. So B tagging therefore is now more commonly referred to as flavor tagging. So we can use the same techniques to identify charm jets, even more recently strength jets, though they have different properties, not usually displaced vertices, but different properties. But one can in principle use the same multivariate analysis techniques to also say if a jet is coming from strange form. And finally, hadronic tau jets. Now, tau algorithms, there were always tau analyses that had dedicated algorithms to detect tau jets. But these are also jets. So why not just use the same kind of approaches as B tagging to do this? So this is what I want to motivate, that identifying jets can be treated as an entire task that does not necessarily need separate approaches for a B detection, for a C detection, and so on. So you can just have one approach that does everything together, and that we are referring to as flavor. So,
Yeah, but one thing, the background should be different for each case, right?
yeah, I mean, for B tagging, your
You
background
want
should
to
be.
have the same framework, but the
But
signal backgrounds are different.
yes, exactly. So you have, if your target is a B, then C is a background, S is a background, tau is a background. If your target is C, everything else is a background. Depends on what you really want to tag and what you want to
You want to have a similar framework.
similar framework for everything. And the light jets, which are like the most common jets, these are typically always your background. So light jets and coming from gluons, you basically have an enormous QCD background in hadron colliders. So these are typically your the kind of backgrounds you want to get rid of, and these are typically your signals. But there are of course exceptions there. Now, why we want to tag this as well? Because since we are getting more sensitivity at the LHC, we are now getting to a regime where we are sensitive to even Higgs couplings to second generation quarks. So if we want to detect, for example, a Higgs decaying to charm quark, a pair of charm quarks, then we do need to identify this as a whole, not just tag them as Bs, but also tag them as Cs. So we need to be able to identify C jets. So in the future, at some point, we'll probably also be sensitive to S jets, so Higgs to S, although this is like in the distant future, but as at least as an academic interest, this is also interesting. And also for standard model searches, we might need dedicated S tagging in some places. And hadronic tau jets are of course extend your tau searches by including hadronic tau jets. So these are also important final states that we want to identify. So how do we do it? You see that a jet is a cluster of particles, like I said, and this order of particles is the number of particles is around 10. So it can be 10, it can be 20, it can be 30. So order of 10. Now each particle also has some associated properties that can be measured with it, like its momentum, its pseudo rapidity, its coordinates, basically its displacement with respect to the primary vertex, tracker hits, tracks quality, and so on. So again, per identified particle, you have like order of 10 measured properties. This can go up to like 15, 20, so order of 10. So when you look at the entire phase space, it's like order of 100, so something between 100 to 1000 variables per jet, right? So you see, there is one different kinds of jets, and you have signatures in the end. You have like 100 order of 100 inputs here. So this seems like a very natural playground for multivariate analysis techniques, which means you include all this information into some kind of tagger or some kind of algorithm, and you want to predict if it's coming from a B quark, C quark, and so on. So there are different signatures. It's of course not. It's possible to use physically motivated variables, but it's probably a better way to simply put all this information into a neural network and see how good it will do. And turns out this is indeed a better way than using physically motivated variables alone, like I will explain. So before going through all the steps, I'll give a spoiler here. This is the latest performances, latest plots from the Atlas collaboration and from the CMS collaboration. So let's spend some time on this plot because it says a lot. On the x-axis in this, it's year. Run 2 and run 2 recos were until 2020. Then beyond 2020, we started with LHC run 3. So we can like almost divide this into run 2 and run 3 strategies. Similarly for CMS, it goes a bit behind. There are no years here, but CSV V1 was around 2014. Then the rest were in run 2 until 2020, and then the next developments were in run 3, early run 3. So you can think of the x-axis as a time scale, and these are just the names of the taggers that were developed. And here is the real year when they were published. On the y-axis, in green here, you see the rejection of CJet, and in blue here, you see the rejection of lightjet. Now, all these rejection factors, it means how often you get rid of CJets and lightjets while tagging a VJet. So this is all. These plots are drawn with respect to VJet. These are shown for a fixed point, which means you let's say we fix our V tagging efficiency at 70%, which means out of 100 B jets that are produced, you correctly identify 70 of them as coming from B jets. For the rest 30%, you don't identify them. You misclassify them as light jets. Now, using a fixed criterion for B jets, one can see how often you mistag C jets as a B jet. So, or a light jet as a B jet in these two axes, in these two colors. So, let's say we have this number here. Let's say this is 2300 here for light jet rejection. This means that for every 100 B jets, you correctly identify 70 of them, and for every 2300 light jets, you mistag one of them as a B jet. So you can see the order of magnitude here. So out of, if there are 2500, 2300 light jets produced in your experiment, only one of them would be mistagged as a B jet in this ultimate error. So this gives you a hint of how efficient these algorithms are at this point. And okay, and same goes for CMS here. Here, red shows you CJet rejection, and yellow here shows your light jet rejection. So here you also see similar numbers. This is like 2000 here. So for every 2000 light jets that are produced, you would detect only one of them as a B jet, even though they are truly light jets. So this is like, of course, a limitation. Everything cannot be perfect here. This is done at the same criteria that you identify 70% of the B jets correctly. So you see that these numbers have gone up quite a lot. So by a factor of 4.2 here compared to 2017, and a factor of 61 here compared to 2014. So these are like tremendous progress over 10 years. And then what do we see right away from here? And okay, also you notice that this axis here is exponential, so like log axis. So any growth here is pretty much an exponential growth in this yellow lines. So what we see is that experiments have steadily adopted new tagging algorithms over the past 10 years. So you see already like 6 different algorithms reported here just in the 10 years. And we empirically see that our light jet rejection factor is growing almost exponentially with time. And our CJ rejections are growing with time, linearly with time. And both the experiments show similar trends. So everything is evolving convergently. And well, yeah, some is subjective, but some experiments have better choice of colors. So yeah. Um, so also some notes here that this plot shows only half of tagging algorithms that have actually been used. So you see 6 here, but there were around even more than 10 algorithms that were actually developed and tested, and then they were not reported. So this is a very active field, and then the ones that have actually been developed inside CMS or Atlas are actually a very small subset of what algorithms have been proposed in physics, experimental particle physics, or phenomenological particle physics literature. So this is like, yeah, this is like a very small subset of that. And furthermore, the architectures that have been proposed in literature are further a small subset of architectures that have been used by the core machine learning community. So you see that this is a very active and dynamic field of research. There are many scopes here. Things are improving, and new machine learning advances are coming up. They are being used by phenomenological studies, and then they are being adopted by experiments. So this is a very dynamic field. It's evolving with time, and every year you have several papers on this. And yeah, so it's interesting. Now this is a plot that shows inter-experimental comparison. So it's kind of similar, like publication and light flavor jet rejection. So just one parameter to keep our focus on. And then these are divided into runs. So run 1 until 2014, then run 2, then run 3. And then CMS is shown in blue, and In orange, we have Atlas, and ignore this conventions for now. So what we see here, this is again a log scale. So what we see is pretty much an exponential growth here. And even though there are caveats to this kind of comparisons, because you cannot really directly compare these numbers between Atlas and CMS, but this at least shows similar trends between the experiments. Okay, there are numbers, they are growing at a certain rate, and they are similar in both the experiments. So it's pretty much a universal approach. And if you had 10 more experiments, you'll probably see the same kind of approach. Okay, so now coming to the main part, the tagging algorithms that were developed over the years. So the pre-ML era, which means 20, let's say until 2013, when we didn't actually have real machine learning algorithms, just some physically motivated variables used in likelihood fits and so on. So this is early run one of the LHC 2013. These discriminators are typically characterized by likelihood ratios that are built from high-level fixed motivated variables. So like I said, there are secondary vertices. You try to reconstruct secondary vertices. You see how much what the flight distance is, what the displacement of the tracks are, and fit them into a likelihood ratio to see what probability of the jet coming from a peak fork is. So basically, secondary vertex kinematics, track kinematics, multiplicities, and so on. So this is a typical discriminator output. It's called CSV in CMS. So this is a score that goes from 0 to 1, and it's devised in a way such that the more B-like the quark is, the jet is, the more it will shift towards 1. So you see B jets are shown in red here. B jets start to peak on the right, which means that this is doing what it's supposed to do. And this has a certain degree of separation. P jets are moving to the right, and line jets and C jets are moving to the left. So this is like a early likelihood based approach here. So as an example, CSV V1 in CMS, this is a likelihood ratio based up to 8 tracks and secondary vertex variables. So just 8 variables going into this and giving this discriminator as the output. Similarly, in Atlas, there was IP and secondary vertex based two different likelihood ratios that were using IP and secondary vertex informations, and they also had similar discriminations. Now coming to the core ML era, beyond that, so we can view a jet as a table. Like we can view many jets as a table. So let's say we have jet one and we have associated properties. You can think of them as, let's say, the first track's PD, the first track's impact parameter, and so on. And then let's take 4 tracks. Let's say we can take the reconstructed secondary vertices, PT, displacement, and so on, and also the jet global properties. And then in simulation, you have the true information whether your process had a weak fork or not. So in simulation, you have a table of jet properties like this, and you have the truth information to that. So you have a one-to-one mapping with the truth information and the jet inputs, right? So this you can recognize this already, that if you had if you were doing a typical machine learning application, if you had data like this and you had to predict this category here, you would fit this simply into a BDT or a simple neural network, and you would probably get your results. So as long as you can view jets as a table of data, you can use BDTs and shallow neural networks to do this. If you have experience in machine learning, you probably have done this with Spandas data frames and things like that, right? So what are boosted decision trees? They're basically an ensemble of weak learners. So there are individual learners that or individual decision tree that makes a prediction based on a certain property, and then all of these are combined into one ensemble decision, and it's basically called a BDT. It's like a flowchart-like structure. And then, as long as you have a table of data, you can fit a BDT algorithm using that. So BDTs are okay. So that's what BDTs are, and then shallow neural networks. They are also something similar that work on tabular data. They are like neural networks, but very simple. Just one input layer, so seen here, and one or two hidden layers, seen here, and then one output layer with multiple nodes. And the number of nodes here are typically small, like order of tens. And these are characterized by fully connections, like every node is connected to every node in the next layer. So these are called dense feed-forward or fully connected networks, also known as multi-layer perceptrons. So these are like the simplest kind of neural networks that exist. And these are this kind of architectures, BDTs and shallow neural networks. These are suitable for tabular structures with 10 to 100 inputs. This work very work well. So as examples, CMS used an MLP with one hidden layer. This contained 22 inputs with 4 tracks and additional variables. So this jumped from 8 to 22 with the use of machine learning. And this is the improvement you see based on that. So you see you had a light check rejection factor of something. Let's take this as our reference 1. And that goes up by a factor of 3.3 when you switch to ML. So you go from 8 inputs to 22 inputs, and then that gives you a factor of 3.3 in terms of rejection of light jets. Same goes for Atlas. They also had initially an MLP with 2 hidden layers, and they combined the outputs of lower level taggers. And then next, they had a BDT architecture with, instead of combining outputs of previous likelihood taggers, they just used all low level inputs. So 24 low level inputs as compared to CMS's 22 inputs. So similar kind of architectures, and therefore it can leverage correlations between all the inputs. And yeah, so basically both the experiments at some point in 2015 around that moved to ML, and this is the kind of jump you see. Then there are other examples as well. Just quickly going through it, there are lepton-based taggers using BDTs. There are BDTs in CMS to combine outputs of other taggers to give you combined output. Then dedicated C tagging. There were dedicated BDTs trained for C tagging, which means one dedicated BDT that was trained to discriminate between C and light jet. So again, a binary classifier for discriminating between C and light, and similarly C versus B. So two different BDTs for that. And Atlas similarly had a jet feeder algorithm, which is a shallow neural network with 8 inputs and so on. So these are all examples of shallow neural networks, and they all showed improvements over previous approaches. Then
but the shallow networks didn't have the option to do this multi.
Yeah, in jet feeder actually they did. So there is nothing stopping you from adding 3 nodes here. There are 2 here. Nothing stopping you from adding just 1 node here. And in Atlas, they actually did this. In jet feeder, they actually did a multi-classification with VC and like that. So in principle, it's extendable, but back then there was no use case for C tagging in principle. Like when CSV V2 was being developed, one did not think about C versus C versus B. So this was developed separately. So it's just historically different, right? Then coming to generation 2, this is like early deep neural networks. So we can still think of jets as tabular data, but this time instead of let's say 10 columns, we think of 100 columns, order of 100, or several tens, let's say 60, 70 of columns there. So in that case, simple neural networks are no longer powerful enough to handle all that data. So we move to so-called dense deep neural networks, which look like this. You have an input layer, several hidden layers, and then an output layer, and everything is connected to everything in the adjacent layers. So a fully connected deep neural network. That's the first early deep neural network approach. Then instead of tabular data, you can think of a jet as an image. So this is a image I took from some paper. Where they average over a lot of jets and see what the jet typically looks like. So this is what a jet looks like. You can think of jet as different hits on your detectors. So there are several particles, and you just see the particle. You can think of this as a camera just looking at the jet. So you can think of it as a picture, and then you try to classify it. So this is where computer vision comes into play. Convolutional neural networks are known to work very well with computer vision. The idea is that you have an image, let's say it's your face, and it's 10 faces, and then you want to recognize yourself from those 10 faces. This basically does this using convolutions. So you have grids here which go over the image, then creates a latent feature map, which is pooled, and then you create further feature map. This can be stacked. These operations can be stacked on top of each other, and in the end, you pool them together, and then you pass through a simple neural network. So this is a very well established method in machine learning, computer vision, and so on. So this has been in vogue for several years now. And then since you can view a jet as an image, this is a technique that you can use on top of this. So you can basically move your convolutional layers on top of this and view the jet and say, is it coming from a B jet, is it coming from a C jet, is it coming from a light jet, and so on. So this is how computer vision comes into play here. Then going further from that, instead of a image, you can also think of it as a time series. So by time series, you mean, let's say you have stock market numbers, something goes up, something goes down, and there are different factors. So you train a time series by using these factors as your input and your stock market valuation as your output, for example. So this is where time series analysis comes into play. And it was seen in machine learning literature again that recurrent neural networks, things like this, are good at time series analysis. So what this does essentially is there are n of these in n gates like this, n units like this, and each unit has a input gate. So this takes as input the n minus 1th term in your sequence, and then it determines which of the information needs to be forgotten, which needs to be retained, and then puts this forward and passes it to the next unit. So your n minus 1th unit combined with the nth unit gives you your n plus 1th unit. So this is upgraded in a way that it gives you, minimizes your loss and gives you your best prediction possible. So in case of jets, you can think of a jet as a series of particles which have been ordered by a certain motivated variable. Maybe let's say PT motivated, or PTs of the jets of the particles, or the impact parameter of the particle, or something like that. And then this is a variable length sequence. A jet can have 5 particles, can have 20 particles. So it's a variable length sequence, and you can pass this through an RNN to give you a prediction. So if you treat a jet as a sequence, this is also a possible way, and RNNs come into play here. So we look through tabular data as an image, as a sequence. So DNNs, CNNs, RNNs. So you see that all of these can be used for jets, because jets can be viewed as several things. So keeping all of this in mind, CMS, this is one example again. CMS developed the so-called DCSP algorithm, which is views jet as a table of data, and this is just more data, so like 66 inputs instead of 22 now, and it has 4 hidden layers, so a larger network. Each layer has 100 nodes, and it takes as input features of up to 6 tracks. And by doing this, you see that we jump again from a factor of 3.3 to a factor of 6 here. So again, a factor of 2 jump. So just by adding more inputs and having a larger network, we see a significant gain here. And what was done simultaneously, like just now I was saying, that nothing stops you from adding more nodes in the output. So you can use the same network to predict not just B but also C, or if 2 B quarks are present inside the same jet, and so on. So instead of a binary classifier, this is the first time CMS moves to a multi-classifier architecture. And then C tagging can be done by transforming the outputs as you need. So this is typically how multi-classifiers are handled. Same goes for Atlas. They developed the so-called deep learning 1 algorithm, which uses 8 hidden layers, where each layer has 76 to 6 nodes. So funnel-like structure, and it includes up to 28 inputs, including tertiary vertex properties, which is motivated by the presence of C quarks, if any. And then this also acts as a multi-classifier with B, C, and like nodes. Okay, then going beyond tables, now let's also treat them as sequences, not just tables. So RNN-IP is a network that Atlas developed. This is a network with information of up to 15 tracks per jet that is expressed as a variable length sequence, and you put it through an RNN. So 15 information of 15 tracks goes through an RNN and gives you an output. So this was seen to perform similar to DL1. However, what you can do further is take the output of this and put it into DL1. So this gives you like 3 output classes or 4 output classes. You put this as additional inputs to DL1, and you get DL1R, which is like a combination of tables and RNNs, so tables and sequences. So this has a larger number of hidden layers because it handles more data. And when you do this, you see that compared to just a tabular kind of representation, when you include tabular data plus RNN structures, you jump from a factor of 1 to factor of 1.4. So it's the same data with maybe some additional information, but you handle them in different ways, and you exploit the correlations, and you get a better network here. And of course, you need to increase your network size for that. Okay, now we talked about DNNs, about RNNs. Now let's also look at how CNNs can be used here. So DeepJet is an algorithm developed in CMS. This treats jet as a collection of different kinds of objects. So jets will have charged particles, they will have neutral particles, they will have reconstructed secondary vertices inside them, as well as jet global variables like jet PD, jet beta, and so on. So you can use all this information separately. So they used convolutional neural networks for each of these categories. So you basically, okay, they also use 25 charged particles with 16 features each. So you see that this is already a huge number, 16 times 25. So this is typically not suitable for just a direct DNN. This needs to be scaled down. So for that one uses convolutions. Convolution neural network, this scales it down. Then since this is a variable length sequence, you can take up to 25 particles. This can be 5 particles, this can be 10 particles, this can be anything. But you can take up to 25. It's more than 25, is trim it to 25. In any case, since this is a variable length sequence, in theory, if you pass it through an RNN, you probably get something more um, because you treat this as a time series as well, not just as an image. So that's what they did. They passed it through a convolutional neural network, then through a recurrent neural network. Same goes for neutral particles, secondary vertices, different number of features and different number of particles that are taken, and then the global features as well, concatenated later on. So this reduced dimensionality is then passed through RNN, and then all of this is fed into a dense neural network, and then it predicts the output classes. It includes B, C, light, along with different types of Bs as well. So CNNs basically reduce dimensionality, and then you pass the variable length sequences through the RNN, and then finally you concatenate all these categories with the global variables, and you get 6 output nodes through the classifier. So this was a big jump because this, for the first time, used everything from the low level and reduced the dimensions and then did the classification. So this
through this evolution, so but you also need to have more input data, right?
yeah.
So
So
millions of events for training and
yes, that's also true. So you also need to train this on larger amounts of jets. Otherwise, you just overtrain on few jets. You just learn the jets by heart. So you don't really extract the features. So yeah, of course, with this you need more larger data sets.
So with shallow and BDD NN for likelihood, we were fine with using the very less number of
Yes.
events, but with the more input features and also more low-level information.
So we use the larger networks we use, the more data we need, because if you have
millions of simulated events.
millions of similarity events, exactly. So if you have like 300 jets and then you have a network with 1,000 parameters, the network will just memorize 300 jets. So that doesn't really help, right? So you need at least as a figure of as a rule of thumb 10 times more data than the number of parameters, right? So this then deep jet basically again increase the performance. This goes from 6.1 to 19, I think, yeah. So this again was a factor of 3 jump. So this was pretty significant in run 2. Okay, so this was generation 2, where we looked at jets as large tables, as images, as sequences, and so on. Next, we go to generation 3, where we start to look at jets as sets, point clouds, and use transform architectures. Now, why do we do that? Whenever you look at jets as a sequence, and you impose some kind of order, because a sequence needs to be ordered, then you are manually imposing a order that's not really physical. You are manually using some kind of number that you are assigning to make the order. So this is not a natural way to represent a jet. Instead, if you represent this as an unordered set of particles, this seems to be a more natural representation. Jet constituents do not have an inherent ordering. They are just particles that are available in the detector, right? So this is where third generation, like I would classify them as third generation. So deep sets is an architecture that does exactly this. Is the permutation very invariant operations are done. So this is called a set function. It can be something that's as simple as summing things up. So summing, as you can imagine, there are 10 entries. If you sum them up, it's permutation invariant. You order them in any way, it doesn't matter. So that's where this new ideas came to light. Then when you apply this set function, you basically reduce whatever number, n number of particles to just one representation. It's as simple as just summing them up, for example. So from variable size inputs, you get a constant representation of jets, and this basically the idea was that this should improve generalization or instead of imposing and ordering there. So this was proposed back then. Then, in parallel, there were developments of treating jets as graphs or point clouds of particles in a 3D phase space or a 2D phase space, or even actually a 3D phase space, not necessarily eta phi plane, but in a 3D space. So you can think of a jet as a single graph where there are n nodes, so n particles correspond to n nodes, and any interaction between two particles. So you can, for example, take any two particles, you can calculate the distance between them. You can calculate, let's say, there are two muons, you can calculate the invariant mass of these two. These are physically motivated variables. Just an example. So you can compute pairwise interactions between them, and they are naturally a edge of a graph. So n number of nodes and n times n connections. So everything is NC2 connections. So order of n squared connection between them. So that can be interpreted as edges. So graph neural networks are specific neural network architectures that learn from that kind of particularly that kind of input data. So this is how things would look like. You have the circles as your nodes, so particles in your jet. Everything can be typically connected with everything else. This is just a non-fully connected graph. But you can in principle also connect a fully connected graph, create a fully connected graph. Then there are GNNs, which handles this in a way such that not only the nodes but also the interactions are taken into account, and then you can eventually pass them through so-called graph convolution networks and so on, and then finally do a classification to get your output. So you can imagine jets are a perfect candidate for this because they are exactly this kind of graphs, and you can in principle use this kind of data structures for that. Now, going further, that is a simple graph that I said. You can do more with that, or you can do special smart interactions, not just simply use GCNs. So there was something was proposed. This was a very, let's say, a very prominent paper. An operation called H convolution was proposed, where you transform each node, let's say xi. Xi can have you can calculate the nearest nodes to xi, right? You can calculate 3 nearest nodes in this example. You can calculate 10 nearest nodes if you wanted to, and then based on the properties of this node as well as these nearest nodes, you perform a convolution and you get a transform representation. So one H convolution operation gives you goes from xi. I mean xi goes to xi prime. This is just one H con operation, and this is stackable. You can just make sequences of this. So you can have a network that constantly changes xi to xi prime to xi double prime and so on, and you can then the network has more freedom to learn various kind of abstract representations. So you can think of a higher dimensional space where from this space it gets transformed to a different kind of space. This gets transformed to a different kind of space, and these transformations are learned by the network. So these are these HCOM operations are learned. And you can keep doing this, and you can combine all these kinds of representations to a single by a single pooling operation, and then pass it through a neural network to get your outputs. So essentially, you have these convolutions, you have these transformations, which can be learned. So the network will learn to transform them very smartly, the smartest way possible, so that this gives you the best discrimination. So this was pretty much a revolutionary technique in field of jet tagging, I would say, because this gave a huge jump in terms of tagging performance. So yeah, beyond that, next came attention mechanisms and transformers. So you may have heard of attention is all you need, a paper in I think 2017, 2018, which basically ushered the era of transformers. So you have ChatGPT, you have Meta AI, you have a lot of AI stuff. All of them have transformers. GPT stands for transformers. So transformer was pretty much again a revolutionary technique that was developed in machine learning field, and we can in principle adopt them for us as well. So what does attention mechanism means? It means that instead of treating sequences like I was like I was saying, that you have one sequence going into an RNN unit, then the next unit is treating it. Instead of that, this attention mechanism basically relates all the units in all the tokens in the sequence with each other, and then assigns importance to them. That is assigns a weight to each of them. So these weights called as attention weights are computed on the fly during the training, and then if something is important in a sequence, it gets a higher weight basically. So this captures context effectively. You can imagine this in natural language processing. I have a big sentence like, let's say, my friend is coming to visit me. So of this, friend is probably an important word. Is probably not such an important word because it's usually common. So the context gives you friend and visiting. So in this sentence, if you had to process this using NLP, you would get a higher weight for friend and visiting, because these are your main stuff in the sentence. Is not an important sentence. It could be are. I mean, that would be grammatically wrong, but the network doesn't care, right? So this kind of things would not be considered important, but the main things would be considered important. Same goes for jets as well. If there are long sequences of particles, jets, this kind of networks assigns higher weights to particles or to parts of the sequence that are more important. So this might seem like a very trivial thing, but this actually has huge implications. Then transformers is basically uses this kind of attention mechanism to process entire sequences at once without relying on recurrence relations. So it's not like one token is processed, then the next token is processed, then the next token is processed. This is slow. Instead, you have transformers basically analyzes and encodes the entire input, processes the whole thing together, and generates outputs. And this can be parallelized. So you can have multiple attention heads, the so-called attention heads. So basically, multiple processors doing this for you. And again, this was again revolutionary in the sense that this basically ushered an era of chat GPTs. So so yeah, so all these ideas can be used in jet tagging as well, as was shown. So I'll again go through all of them in a sequential way. So as
How does like the admission mechanism? How does it know that it's a relevant one to keep?
yeah, that's what it learns from the training, right? It learns, okay, this kind of if a particle has this kind of features, is more important for me.
So what's hidden behind? How does it learn?
It learns biases. Yeah, in the end, it's all just biases and weights, but then you have a larger number of parameters. So it's just a model, but it's just like a DNN, but a more sophisticated way of putting them together.
What is the sophistication which is learned?
So for that, I will have, okay. Honestly, I don't understand the details in the ML from the ML perspective, but it's like you have a bunch of you have a layer encoding, you have a ML, you have a multi-layer perceptron together, and this forms your transform. I don't understand the full details, but this they showed that this helps you encode the whole thing together and then generate the output. So it's just a complex network that does the encoding and the outputs together. So it's not. I mean, yeah. Basically, it's probably very profound in machine learning world, but I don't understand the details. Right. Yeah.
So, in a jet, so what would I expect it to assign more importance to? Like, for example, in the sentence you said that friend should be assigned a
Yeah.
importance.
Yeah.
So, is it like higher energy or heat?
No, it's okay. That's again coming to feature importance rankings. These are something that we've actually that people do already. So in a jet, it's typically the more displaced tracks are assigned more importance. So if the more displaced it is from primary cortex, the more likely it is to get weak form coming from weak form. So these kind of things are learned by the network. So yeah, so jets, that's the kind of things you would expect to learn. So again, these are you need to interpret this correctly to get your. There are techniques to interpret and look into the network to answer exactly this question: that what it's learning, what is it learning, and why is it learning that. So yeah, basically you would expect at least from a physical intuition that it would learn that is to focus more on displacement of the tracks from the primary cortex and so on. Yeah. All right. So then, giving some examples again for this kind of architectures. So, like I said, there was this the deep set architecture. So Atlas developed this DIPS neural network, which is basically does this summation operation over all the individual tracks, and then some dense neural networks and 100 nodes each, and it classifies as BC-like. So turns out when you have this deep set architecture instead of the older generation RNNs, it gives you same performance, but with fewer training parameters. You have the same number of jets as input for training, but with a fewer parameters and faster inference time, you get almost the same performance or even a better performance. So what we see, RNN depended on a imposed order because it needs a sequence. Deep set does not need a sequence; it's just a set which does not necessarily need to be ordered. So since this is a more natural representation of a jet, turns out the network learns this more easily. So when you have network, when you have a representation of a jet that's more natural, it turns out you learn the same thing, you will have a similar performance, but you do it more efficiently. Because the number of information is probably the amount of information learned is probably the same, but you learn it in a more efficient way. And then, in the same way as RNNs were included in the Atlas algorithms, this deep set was also included as an algorithm. And you see, there's a jump here again from 1.4 times to 1.7 times. So this might not be very high, but you see, with just a different way to treat jets, you get an improvement. Of course, here they might have used um, larger networks, but in any case, you get faster training and faster performance. Okay, now until here, like I said, this deep sets are trained here and again added back to this initial network. So this network is augmented with different kinds of information, different kinds of networks. So Atlas so far did not have a single network that goes from raw inputs to the full classification. So that's why the next improvement comes in run 3. Atlas developed the GN1, and for the first time, it's an end-to-end approach of flavor timing. So it does not rely on different kinds of components and then merge them into one. Instead, it does it from end to end. So starts with 21 properties of up to 40 tracks per jet. 40 is already a large number, so pretty much all tracks in a jet. So it uses like 800 order of 800 information, and then directly does the goes to the network. So there is a per track neural network which projects the track into an abstract phase space, followed by GNNs with these embedded tracks. There are three layers of GNNs, and this is 20 to 30 million jets. So we are in the range of tens of millions of jets now, since these networks are expanding and becoming bigger. And what's new here is not just in the same network, they don't just do flavor tagging, they also predict other things, such as where did this particular track, okay, so track number n, what kind of particle did this track come from? Did it come from, I don't know, pion, kaon, muon, whatever. So this is trying to predict the origin of each track individually. So every node in the graph is assigned a category of which kind of particle it might have come from, and also compares every edge in the graph. So every pair-based particles, it takes every pair and tries to predict whether these pairs are coming from the same origin. So this is a sort of a vertexing method, an implicit vertexing method. It turns out when the network has additional things to learn, and these are physics motivated things to learn, this actually helps the classification improve. So this is a completely different task, but if the network is trained to do this kind of physically motivated task, it improves the classification in turn. So this is a very interesting thing that including physics in your network, not just blindly putting in information and getting out an output, actually helps improve the performance of classification as well. And here again, you see this is a phenomenal jump. It goes from almost 1.5 times jump from the previous generation. Then going further, GN1 was replaced with GN2 again in run 3. GN2 now includes a transformer architecture, and this is the state of the art for Atlas now. This from 3 layers it goes to 6 layers of GNNs, and there are around 1.5 million learnable parameters with 192 million jets being used in the training. So we are now in the range of 100 million jets. Now this may seem like a simple thing, but it's computationally challenging to actually generate all these jets and train on them. Training time gets longer, generation time gets longer, and so on. And this actually shows that when we introduce transformers, and of course transformers are data hungry, so you can keep feeding them a lot of data and they will keep improving. So transformers are known for being good at handling large amounts of data. You see, this is a huge jump, goes from 2.3 to 4.2. So the state of the art currently is like a factor of 4.2 from what we had in 2017. And this is in absolute numbers, this is like 2,300 rejection factor of light jets. So what we see here is that if we use larger amounts of jets as input parameters and we have a large model, then it simply keeps getting better. We don't know if this is saturated. We can probably use 1 billion and maybe it improves. We just don't know at this point, right? Similarly, in CMS, now coming to CMS, particle net, like I said, was a big step. So particle net was this dynamic graph convolutional neural network based implementation. This has like edge comp operations. It uses 16 nearest neighbors. And for the first time, CMS introduced a hadronic tau mode in its flavor tagger. So this is going towards unified taggers. and a hybrid loss term that is not just does the classification but also does the finds out the energy of the jet. So does a regression of the energy along with the per jet energy resolution. So this again showed an improvement. So it goes from 19 to 29, I guess. Yeah. So some improvement here again. Then finally, the state of the art for CMS is called the unified particle transformer. Now again, we get into transformer architecture in CMS. This is again based on attention mechanism with multiple heads, like I said. And then in this case, you have two kinds of inputs. Like I said, there can be particles, there can be pairwise interactions. This is of the order n, this is of the order n squared, so like NC2 interactions for n given particles. And then there are additional things like so-called adversarial training to improve robustness, and I'll explain this. And then unified, it also includes hadronic tau nodes, S-jets nodes, jet energy regression resolution, and so on. So this is why it gets then unified. This is how the architecture looks like. I'll not go into details, but it's like stacked attention blocks. These attention blocks are basically the attention values are modified based on this embedding. So embeddings, the interaction embedding. So pairwise interactions are used to augment the attention weights that are calculated, and then they are passed to a class attention block, and finally a neural network to classify. Okay, and in this training in CMS, around 30 million jets were used compared to 192 million in Atlas, and one goes from a factor of 29 here to a factor of 61. So it's again the similar trend. You get a jump of a boost of 2 times compared to previous architectures, right? And this is like 61 times what we had in 2013. So this is like a phenomenal upgrade here. So, like I said, this has additional nodes. So there is a modified loss function where you simultaneously do classification, regression, quantile regression, and you see that this gives an improved response. This is the median response, and it's close to 1. So details I won't go into that. Then adversarial attacks are a way to deliberately introduce mismodelings into the input, so that the network learns not only the simulated values but also their perturbed inputs. The idea behind this is that between simulation and data there are differences, and if the network learns small changes in the inputs and still remains robust against those, then maybe in data any differences in data are also absorbed, and it's also better performant in data. So this is a pilot project. This was introduced in unified particle transformer, and if you look at the ROC curves, I don't have time to explain this, but you will see that the adversarially trained network is more robust against small perturbations in the inputs. Then yeah, like I said, it's a multi-classifier, so it does C tagging, which has improved over past taggers. It does S tagging, so this is for the first time one sees S tagging performance, and it looks like you can have a low efficiency strength tagging in CMS at some point. Then there is tau tagging as well through the same network, but these are just plots to show you that this actually works. So to summarize where we are standing currently, okay. So now all algorithms in CMS and Atlas are end-to-end. So you use particle level features as input, and then use all particles, and you try to predict the outputs. Architecture, we have convergently evolved towards transformers. So transformers are the present and probably the future as well. Then we are going towards unified taggers. We have auxiliary tasks to augment the classification performance, and we also have robustness against mismodeling using adversarial training. So next is calibration. Now, why we want to calibrate these flavor taking outputs? The reason is that we use simulations to train our networks. So there are mismodelings in inputs. This is just one of the inputs that are used as inputs to the network. You see, when you compare data versus simulation, they are not flat. They are not at one. There are significant differences. And of course, if the network learns from simulation, the output of the network will also have differences. So this is quite intuitive in that sense. So input, this is the output. One of the inputs has discrepancies. Many others will also have discrepancies, and you see discrepancies in the output. Therefore, we need calibration. Now, traditional ways of calibrating is to put a cut on this at whatever efficiency you want, and then beyond that, you try to calibrate the bit tagging efficiency by a number. You scale it up by a number, scale it down by a number, and so on. These are called scale factors. However, more recently, we have CMS and Atlas have tried to use machine learning here. So deep scale factors is a way to predict the scale factors by a network, and then a discriminator discriminates between simulated jets augmented by a scale factor, and real jets from data. And then the producer network updates itself using this adversarial attack. So a discriminator and the producer works adversarially against each other and then produces scale factors until the scale factor applied simulated jet starts looking the same as jets from data. So this is a typical adversarial training. And this gives results which are compatible with traditional methods. So there are problems here. Adversarial setups are difficult to train. They're notoriously difficult to train. Basically, you need to find the correct hyperparameters, and it's very difficult to reproduce the results with newer data. So you have new data every year, and you have to tune them very meticulously. So it's not practical. Then, more recently, it's a paper from a few months ago. Atlas used the so-called optimal transport method. Optimal transport's goal is to find the least costly path to move one jet in this 2D plane to a new number, so that the updated one resembles data. But this has to be done in a way that's least costly, so that movement in this 2D plane is the smallest. So this is the idea of optimal transport. So in this case, the discriminator scores themselves are updated. So you can think of this as simulation, you can think of this as data, and then you move each jet from one point in this 2D plane to another point in this 2D plane. And however, this needs to be done without affecting other physical variables like jet PD and so on. So this needs to be done in a conditional way. And the so-called partially input convex neural networks are used for this. This basically predicts a scalar convex function, and it is known that optimal transport is basically a derivative, a gradient of a convex function. So instead of predicting the transport directly, it predicts a function whose gradient is the transport. So the gradient, so this is predicted with the neural network, and its gradient gives you the transformation map. So why do we do this? Because predicting this convex potential using PICNNs is more stable than the previous adversarial method that I showed. The cons here is the current method uses only a limited sets of data and just one iteration, which might not be ideal, and it's doubtful if it actually extends generally to other selections. But this is again work in progress, just published as a tech report a few months ago. Now, just some quick considerations. I'll just be quick. So, one question that keeps coming is that are we reaching a plateau or a saturation with the current architectures? So, Atlas now uses 192 million jets, CMS uses 30 million jets for the latest trainings. Are we reaching a plateau that if we increase the number of jets, increase our network size, do we improve? The answer is actually yes. There was a phenomenological study here in the particle transformer paper. So you see that these numbers going from 2 million to 10 million to 100 million, we still keep gaining in terms of performance. So beyond 100 million, no one has really seen, no one has really quantified this. But 30 million definitely has room to improve. If we go to 100 million, we see room to improve. Even if we go to 1 billion, we don't know if it improves. We know that transformers are data hungry. They can handle a lot of data. And so far, there is no evidence that we're hitting a plateau with transformer architectures. In fact, with 10x more jets, let's say we go to 300 billion, we do expect an improvement in performance. But then, what are we limited by? We're limited by computing capabilities. More jets means larger networks, means more computation, long training time. So now it already takes weeks to train one of this with a state-of-the-art GPUs. One needs large and fast storages to access them because hundreds of millions of jets are difficult to store, and they have to be in fast storages. And so far, either no hyperparameter optimization is done, or a very simple hyperparameter optimization with reduced model size is done, which is not perfect, of course. With hyperparameter optimization, we might even gain more. So, if we had better computing in the future, we'll probably see improved tagging. Now, reliance on simulations. We rely on simulation, like I said, for supervised learning. Domain adaptation techniques can be seen as a simulation, as a solution. But then changing detector conditions means these have to be retrained every time, so these are not practical. So there must be newer calibration strategies that can be applied a posteriori, not during the training. So and again, whatever gain we are seeing in performance, does it apply to data as well? Does it fully translate to improvement in data? Does it partially translate? Does it proportionally translate? We don't exactly know until we actually derive scale factors for all these new networks. And at some point, we can fear that we'll start to learn only simulation-specific features. We don't actually learn physics, but some simulation artifacts that are only present in simulation, not in data. And there's no point in learning them, but at some point we'll probably start learning them. So can we avoid that? Can we do something else for that? Then, since jets are simulated using sharding algorithms, can we instead use more modern networks to learn from data directly to make to simulate our jets instead of using pattern shower algorithms? So these are good questions. Then interpretability, like the question was, how does a network predict a B jet as a B jet or a B jet as a light jet or vice versa, whatever. So feature important studies are something that needs to be done. These have been done in the past, and unnecessary inputs have been removed and shown to give similar performances. But this needs to be done at the experiment level more often. And which variables contribute most to data simulation mismodeling? Should we remove them? Should we fix them? So these are, we can also improve simulations from this flavor tagging insights. Then we want faster architectures. Like we said, we are limited by computing power. So current transformers which are scaled quadratically, there are newer architectures that scale linearly with number of inputs. So these architectures can be adopted here, and then the advantage, this will probably give us same performance. But the advantage is this will let us use larger data sets, which means we, even though we get the same performance with the same size of data set, we can afford to use a larger data set in the first place. So we can perhaps have larger models with even better hyperparameter optimization. So this is something we want to test in the future. Then calibration ideas. So we can take inspiration from generative modeling. So this is my chat with Meta AI. So I just said, imagine a zebra that looks like a giraffe. So if AI can do this, we can of course use similar technologies to imagine a simulated jet that looks like a jet in data. So like I said, PICNN was one way that Atlas did it. We can use more recent architectures like diffusions, normalizing flows, and so on to achieve these kind of things. Then we can also associate it with just two sets of data. We can do it with many simulated and real jets in different kinds of selections, 3D bar, QCD, B and D selections, C and D selections, and so on. And we can make it conditional on many more variables, ideally a lot of variables, but this needs to be seen if it's feasible. And of course, this must be easily adaptable to collision data that's collected every year. This cannot take 1 year to just calibrate. So this needs to be fast enough. So to summarize, we have seen tremendous improvement in jet level tagging from run 1 to run 3, leveraging the power of machine learning. Jets have been interpreted in different ways as tabular data, images, sequences, graphs, and so on. And this is like, I hope I could send this message that this is a very active field with several papers coming out every year, several new architectures being proposed and being adopted. In fact, every year you see a new publication, even from the experiments, not just phenomenology side. And machine learning has been leveraged in calibration. This is a very nascent stage, but I personally foresee this as a very active way to active developments in the future, and this should be very useful for the experiments as well. And in my understanding, and all the evidence suggests that we are far from hitting a plateau even with the present architectures. So with more computing powers, we can probably have even more improved tagging and novel tagging algorithms and calibration techniques over the years. Next year. Thank you.
Thanks a lot, Sunil. Does anyone have any questions for Sunil? Any more questions? Yeah, so I have a couple of questions. First is regarding this scale factors. You told you take this adversarial attack and then get the scale factors. But like, how is it going to be useful for an analysis? If I'm an analyzer,
Yeah.
and how will I implement that in my analysis?
Yeah, so this network simply, so this is a very simple neural network which takes the jet variables, these are high level variables like PT, eta, discriminator score, and so on, and it just produces a fixed corrected score. So you give the jet PT, you give the jet eta, you give the B tagging score, it gives you a new B tagging score. So for the analysis side, it's pretty straightforward, you just make a new difference. So if this worked as expected, it would actually be easier than applying scale factors.
So then, as an analyzer, I need not like add an extra layer of this thing to add additional scale factors for all my simulations.
Yeah, exactly. So this will probably be implemented as a product. In this case, it was implemented as a product of scale factors for every jet. So if you have 5 jets, you just apply this network on 5 different jets, get the outputs, and multiply them as scale factors. That's all.
It will by default come in my nano already.
Yes.
And only like probably I'll add it like multiply it depending on the number of jets I'm using in my signal or control region. I just use it.
Yes.
Okay, so then I need not like add an extra
Yeah.
piece of framework on top of mine
Yes.
and then get the
Yeah.
scale factor score based on basically the scale factor.
Yeah. If it were that easy, then yes. But unfortunately, this is not stable, as we have seen.
Yeah, but like of course, like at least something got started, right?
Yes,
So,
yes, yes.
Yeah. So hopefully, like in some time, it will also be stabilized.
Right. Yeah.
And one more question about this feature
Importance.
feature importance.
Yeah.
Like,
Yeah.
yeah. So like yeah, of course, like we got started with Kaushik on this, but like where do like so the feature importance studies like aren't they part of the training itself?
In this first, okay, so these are actually two
Because
different
like
things.
usually in the shallow base network, let's say BDT or NN, we do the ranking, we look at the correlation, and then like the low level ones, like the low ranked ones, which are not contributing much, and we basically get rid of them while developing the training the network itself. But like why we need to do an extra step? Can the developer of the new tagger can they
Right.
take care of the feature importance?
Yeah, ideally yes, they should be able to do this. Like you train your first model, first iteration, you do this analysis, and you get remove the thing. In theory, that's possible. In practice, the problem is these feature importance studies are typically not unique. So you can have 10 different studies giving you 10 different results, but especially because the inputs are highly correlated with themselves. So these feature importance studies for a BDT is in fact, like you said, it's easy. You just it probably gives you by default the feature importance. You just get rid of the last 10 variables or whatever. For a transformer network, it's not that simple. In fact, we don't know which method works the best. There are integrated radius methods, there are sharp analyses, and so on. So, for transformers, it's not trivial. We don't even know if there is one fixed method, one fixed algorithm that gives you correct results. We can have stochastic approaches like sharp. They might give you some result, but they're not straightforward. It's not as simple as a BDT that just gives you an output. It's a pretty computationally heavy task to run this on, like let's say 10,000.
So, if I understand correctly, it's basically because the complexity, the
Yes.
way the algorithm is developed, it's not possible for the developer to take care of the feature importance. Uh,
Yeah.
they might do it, but like it may not work for every single occasion.
Exactly. Yeah, that and also the fact we don't know what to use.
Yes.
For BDT is straightforward. For this, it's usually not straightforward. And with this many inputs, it's in fact very like we don't have one single answer that answers this. So there are many ways to do this.
Yeah, in order to tackle it, it will be good to like
Yes.
work on this because
This is a completely
as you go to the complexity,
Yes.
complex situation of developing a highly efficient tagger.
Yes.
So this becomes like extra things to take care of
Yes.
or add, look at.
Yes.
Okay, thanks. Yeah. Any other questions?
Yeah.
So for the graph neural network which you showed, like these edge convolutions, what was the actual physical motivation behind doing those?
Physical motivation was you not only look at a particle as a single entity, but you also look at it as something that interacts with its neighbors. So that was the main motivation, and also the fact that in convolutional neural networks you can create increasingly abstract features. Like you have an image, you transform this into a feature space, transform that into a further feature space, and so on. There is no trivial way to do that with graphs. So with graphs along with this neighboring interactions. So this is one way to do that. HComs are stackable. So this HCom BGCNN paper itself showed that this gives an improvement over standard GCN methods. So yeah, basically to answer your question, this takes care of not just the node but also its neighbors and interactions with its neighbors. Yeah, there was no question.
Yeah. If there are no questions, then let's thank Spandan again and let's hope he will set with his again and give it to this talk too.